All right, previously we looked at, given the equation for a polynomial, what can we tell about its graph? What I want to do here is the opposite. Given a graph, what can we tell about the polynomial? Um, the first question would be, given a graph of a polynomial, can we determine its equation? It's not impossible to do that, but in order to figure it out exactly, you'd have to do a lot of, it could get complicated. But we can determine some basic stuff about it. We can determine whether the degree is even or odd. We can determine the sign of the leading coefficient. And there are a few things we can do that'll give us a lower bound on the degree. So let's just do these examples and we'll kind of talk through what's going on. This first one, we've got, if you look at this, both ends are going down. So that tells us that it's even degree. And the leading coefficient is negative. And we know that because both ends are going down. Think about x squared. And y equals x squared looks like this. And y equals minus x squared looks like this. So if you just think about end behavior there, we can tell that it's going to have even degree and a negative leading coefficient. Now, what about the degree? Well, I think we can look at it and tell this is flatter than a parabola. Parabolas tend to look like that. So we know that the flatter than a parabola, even degree, we know that the degree of this thing has to be greater than or equal to 4. Now, could we determine exactly what it is? Not just by eyeballing it. Could you figure that out? If you had a really accurate printout of this and you did some careful measuring of the exact coordinates of these points, there is a way you could go through and figure out whether it's x to the 4th or x to the 6th or whatever. But that's not something it's not something you can just eyeball from the graph, and that's what I want you guys to be able to do. So we're going to call this all the information we can glean from this graph. All right, let's look at the next one. The next one, both ends are going down again, so just like before, this one has even degree and a negative leading coefficient. But what about the exact degree of the thing, or a lower bound on the degree? There are actually two things we can use to determine the degree. Or I'm going to come up here and write them in. One is the degree is greater than or equal to the sum of the multiplicities. And the other is the degree is also greater than or equal to the number of turning points plus 1. Let me slide that over. I realize it went off the screen slightly. So we can count the turning points or we can count up the multiplicities, and both of those will give us a lower bound on the degree. So for this graph right here, this has one turning point. So that tells us the degree is at least 2. We can look at it though and tell the degree is bigger than 2 because it's not just a plain old parabola. So that would tell us the degree is at least 4. The other thing we could do is come in here and look at it. Here is a 0, and here's another 0. And if you look at these zeros, the multiplicity of this one is 1 because it just goes straight through. This other one is 3 or greater. It's not very flat, so I'm thinking that it's 3, but it's 3 or greater. So if you add these up, 3 plus 1 is 4. So that also tells us that the degree is at least 4. All right, let's do a few more of these. All right, this guy right here, this one, um, its degree is odd. And its leading coefficient is positive. And there are a couple of ways to think about that. If you just remember that y equals x cubed looks like this, I mean, really, we're just looking at the end behavior. So the end behavior of this tells you that it has to be a positive leading coefficient. Another way to think of this is, if the leading coefficient over here, big numbers are getting big and positive. When we come over here, it's going way down. So as x grows large negative, the function goes large negative. So it's acting like x cubed. All right, let's count the multiplicities first. Let's see, that looks like multiplicity 2. This looks like multiplicity 2. And this looks like multiplicity 1. So that tells me the degree is at most 5. I'm sorry. I said this wrong. When you write out this, the degree is at least 5. Why are we saying at least 5? Well, on this one, I'm pretty sure the degree is 5, but the fact that it touches and turns here, that really just tells us that it's even, and same thing here. Well, we can eyeball these and tell that they're 2, 2, and 1. All right, let's also look at the turning points. We've got 1, 2, 3, 4 turning points. So that would also tell us that the degree is at least 5. All right, next one. Let's see. This function here, it goes up on both ends. So therefore, the degree is even. And the leading coefficient is positive. All right, let's count the multiplicities and let's count the turning points and see what those give us. Let's do the multiplicities first. This looks like multiplicity 1. This is 0 of multiplicity 1. That's multiplicity 1. And this one is multiplicity, it looks like, well, it's at least 3. So by looking at those, we can tell that the degree is at least 5. Let me write that a little nicer. Degree is at least 5. Now, if we count turning points, we've got a turning point here, here, here. So we've got 3 turning points. So that tells us that the degree is at least 4. So we've got 2 things here that say the degree is at least 4 and the degree is at least 5. Well, degree at least 5, that one wins. If you think about it, both of these are true. If something is at least 4 and it's at least 5, then the stronger one is the one you keep. Let me explain that one more time because I don't think that was a great explanation. We've got 2 different arguments going on. One of them tells us that we've got at least degree 4. The other argument tells us that the degree is at least 5. So both of those are true. The degree is at least 4 and it's at least 5. So it's at least 5. All right, last example. Both of these ends are going up, so for this guy, the degree is even. The leading coefficient is positive. And if we look at the zeros, we've got the multiplicities look like 1, 1, 1. This one right here, to me, it looks like it's big. It's at least 3. It might be 5. But anyway, we just from looking at it, we know it's at least 3. So that means that the degree is at least, let's see, 3, 4, 5, 6. If we count the turning points, I think that's going to be the stronger thing. Because if we count the turning points, we've only got 3 turning points. So by counting turning points, that tells us it's at least 4. But looking at the multiplicities, it's at least 6. All right. That's it for this section.